Hello, everyone. My name is Alvaro. I'm here to present this ProtoMedX paper that I co-authored with Andre and Plamen from Lancaster University, from the School of Computer and Communication, and Dr. Marwan and Gemma from the Lancaster Medical School. I'm just gonna give you a brief overview of what we're trying to solve here, and then I'll move on to explain the model. Um, so um, after peak strength in our late 20s, bone mass begins to decline and will continue to do so for the rest of our lives. This decline makes our bones more fragile and prone to fracture. And severe cases of this decline are what we call osteoporosis. In Over a lifetime, 1 in 3 women and 1 in 5 men will probably suffer osteoporotic fracture. Sorry. If that fracture is at the hip, the 1 year mortality rate is around 30%. And in fact, in the UK alone, fractures linked to osteoporosis cost the NHS over 6 billion years a year. So I don't know about your countries, but that's a big number. And it's often the case that prevention is better than repair. So what clinicians do now is they normally rely on specialized machines to measure bone health. This here is an example of a DEXA machine. It is the gold standard for measuring bone density and scoring the comparison of your bones to that of your reference population. It generates soft X-ray images, such as the one here on the screen. But it is the T-score here that is ultimately what defines your bone health, which is something that the machine derives making these calculations here. Then clinicians consider other kinds of features like personal factors such as age, sex, and lifestyle, in addition with these T-scores when determining a treatment or a diagnosis. And these same factors are also incorporated in tools like FRAX, which are used in clinics around the world to estimate your probability of sustaining a fracture. The international consensus is that there should be one of these DEXA machines per 100,000 people for an adequate osteoporosis care. However, if we look at international audits, we see that many regions fall short, including the United Kingdom, in fact. We could just say, yeah, just buy more machines, but it's not that easy. These machines are large, they are expensive, and they require specialized training. Scaling up is and will continue to be slow. So when the hardware can catch up, we need advanced techniques to help out. Then researchers are starting to realize, and clinicians as well, that maybe AI could come here to try and solve this problem without needing the DEXA machine, right? So um, essentially, the osteoporosis detection right now, it's what's out there. It's that AI essentially solutions normally just take into account one of the modalities, either only images or only the patient records. They normally forget about the middle class, like it's either you don't have osteoporosis or you do, but they don't take into account osteopenia, which is a condition in the middle, which is the most important to detect for treatment prior to osteoporosis. And then also, most importantly as well, all of these techniques out there right now are what they call black box, right? Like you cannot really get any meaningful explanations that would help clinicians or or anybody. They just explain the gradients of the model. So with that in mind, we were thinking of how to make a model that tries to solve some of these issues, especially the explainability side. And for that, we used this data set that was provided to us through a partnership with the NHS, with a local NHS trust. with more than 5,000 DEXA scans. In this data set, 45% of the patients have a normal bone health, 38% have osteopenia, and the remaining 17% have osteoporosis. Uh, we had a lot of more patient history features, but we focused only on the features shown here on the screen, just to mirror the variables used by this technique that I mentioned before called FRAX. So to solve this problem, first one you need to sort of start with some baselines. So the most common baseline is okay. We take some some of the X-ray images. We select the strongest feature extraction. In our case, that was cross VIT. And then we train a linear classifier or a bit more layers, so essentially like LMLP, and we classify between the three. We could either use just cross entropy between the three classes, or we could calculate that bone mineral density I was mentioning, and then based on that, calculate that T-score and decide whether you have normal osteopenia osteoporosis. So with cross entropy, you get an 82% accuracy, and with the mean square error technique, you get 72% accuracy, which is 10% low. Then for patient records, you could do a similar thing where you use a range of tabular classifiers, including the patient's BMD from the DEXA. So this is the with BMD or without the BMD feature, uh, and predict. So that gives us a bit of advantage if we use the BMD over the vision baseline. But the ideal scenario would be that we would be able to classify with all the images and with patient records uh, to remove the need for having the bone mineral density, which is what comes from that DEXA machines. So the first thing we did was, can we formulate this problem a bit better to get some better accuracy, mimicking sort of the way that this bone mineral density and T-score values are distributed. So for that, we looked back at the T-score formulation, where we can see that the only value that comes from the DEXA machine again is this BMD. The rest doesn't really need predicting. These are things that are out there. Um, so then we can see that this T-score breaks down by different thresholds defined by like the international medical bodies into normal, osteopenia, osteoporosis. So contrary to current work, where we had just that regression or that classification, we do regression for this T-score, either normal osteopenia, osteoporosis, where we just care whether it lands on normal osteopenia or osteoporosis, not the BMD. Uh, so by doing so, we indirectly are predicting the BMD, but we don't really care again about how precise it is. We care more that it lands to a good T-score. And of course, then we add some categorical control entropy as well, so that at the end we can classify between the three categories. So that alone already jumps the accuracy by almost 6%, which is very significant and validate our proposal, but there's still things that we need to do, right? First thing we need to do is putting things together to align more with the clinical practice and start gaining some interpretability. So this is just a very simple process where we just have the backbones that we mentioned before. Each of them gives some latent representations. We fuse them with cross attention because we tried different fusions, and this is the one that worked best as it lets patient records, which are the weak modality, to attend to different features of the images, which are the one that predicts the has the most predictive power. So we just had a simple classification head with our multitask logs, and we get some a bit of accuracy gains. At least we don't lose, but still the explainability problem is not solved. Like if we try to look into some feature importance, what we get is like interesting tabular features that may tell something to someone, but in terms of the images, which are in fact what gives most signal, we just get, feature 295 embedding, is not interpretable at all. Um, so to do that, the thinking process is okay. So what does a human do to learn this, right? So a human or a doctor would go to medical school, right? Or if they're specialized on this, to some specialized practice or training, they'll study the medical theory and medical cases. They'll save some medical cases in their heads, in their memory, and they practice diagnosing, comparing incoming cases to similar cases, and then they'll get like a mental map for predicting an incoming case based on what their memory is, right? It's not exactly like that, but in an abstract definition. So essentially, at the inference time, you essentially see that doctor sees a patient, he remembers the cases, compares diagnosis, and explains the cases. Say, okay, I think you have osteoporosis or something because people with osteoporosis normally have this like patient records, like history of osteoporosis in their family or something like that, and these attributes that I can see on your X-ray. So we try to mimic this process on our model, ProtoMedX, where essentially we train with these multimodal cases. We have a prototype learning objectives to essentially just optimize the representations of the model and find like different separated clusters for each, and save those prototypes in after training, so that we can then use them to predict by comparing ad inference and incoming case to our prototypes, and that gives us not only the prediction probabilities but also the explanation grounded in cases. Um, More in detail, our model, which is called again ProtoMedX, has like this architecture where we have the two encoders that I was showing, similar to the ones in the baselines, and similar fusion as well. But then here is where we can add on our train objectives. This proto that you see here, I'll explain a bit more in a bit, to essentially capture these multimodal relationships and choose good examples, which are prototypes from that latent space that are essentially vectors tracing back to um, training cases. And it leads to us having these prototypes represented in a space, and then again being able to classify through similarity. Um, so, in a closer look, this is what our prototype space would look like. As you can see, we have three separated clusters for the three categories, and it makes like a circle following that continuous nature of the bone health that we were talking about. And each star is different cases or representative prototypes that is learned to classify this, which represent some T-score values, some images, and some records. The way this is generated is again with this prototype loss, which is essentially a classification loss with this separation loss, which is just basically for latent space optimization, which enforces interclass margins, this separation over here, and is the standard adaptation of contrastive learning into prototype learning. And then we also adding this term, the center loss, which what it does is encourages that prototypes are diversified. As you can see here, instead of having prototypes collapsing in one region, which is one common problem of prototype learning, we have them at different points to correctly represent a wide diversity of cases per class. And we also try to have these classes compact in their intra-class distances. And we also enforce these prototypes to be always near the training examples, these dots that you see there, so that we can keep some the explainability there because if imagine this star was here away from the train anchors, then we wouldn't actually be able to explain claim any explainability. It would just be an abstract feature vector. Um, so with that in mind, let's look at the classification heads. So imagine an input where you have an image, an X-ray, and some records. They all get encoded and fused. So then this creates a latent representation. We call it Z, and it will land somewhere here. In this case, imagine it lands where you see it placed. It will be close to this red thing here, which in this case is osteoporosic. So if we compute distances to the nearest three prolines, for example, these three stars, we'll see that it's very similar to these case examples that we learned, which will have some image of what their X-ray was looking like and some of the features of like, what kind of age they were, what sex, whether they had a previous fracture and so on. So that is what leads to us being able to not only predict, but also having that explainability of the model being placed on the screen. Beyond this, we can also obtain, obviously, the classification confidence, which in another advantage of this kind of model is that we can derive this from the voting of the prototypes. Like essentially, we're doing k-nearest voting or k-nearest prototypes, right? So if by the nearest prototypes, whether they are for one class or another, we can sum that and calculate the confidence derived on that, which is another advantage because it really mimics as well the clinical agreement, right? Where an edge case might be one where we are not sure which cases it represents the most, right? Like it might be matching some of the osteoporosis while also matching some of the osteopenia. So we are a bit unsure. And this is another advantage because, a clinician then could be like, okay, my model is here unsure. Let me see the evidence. Let me compare the cases. And then the clinician, can make an informed decision based on also my own knowledge. Um, and you can get all sorts of other explanations or statistics, such as like feature level analysis, where you could calculate by any given input what the feature deviation they have with respect to either the target class or other of the classes to see uh, you know why certain patterns explain uh, that particular classification or that particular prototype. And in fact, in the paper, we made this diagram which sort of shows some of these explanations all together. Um, so that's more or less the whole concept on the model and how it works. So in summary, this in this with this model, we were able to demonstrate that it is possible to use prototype learning in a multimodal setting. In this case, it was tabular and images for this medical case, but it is the first prototype-based model that combines tabular records with some other unstructured modality. And we show that with the proper optimization for this latent space, geometries and so on, that we can actually make these models not only explainable, but have same or even better accuracy than the black box counterparts, which is very important because one of the big limitations of deploying these models in production in many cases is that they tend to trade off explainability for performance. But in this case, our goal as well is to maintain or increase performance. So by doing so, we're getting explainability for free, so to speak. Um, So yeah, as part of like some limitations and next steps, some things that we'd love to explore more are making studies with clinicians to see whether these explanations are actually useful for them in the practice. So I would imagine having some group where some clinicians where you don't give them anything, some clinicians where you give them a black box model, and some other clinicians where you give these explanations and see which ones do better and feel more happy and so on. And of course, making this more of a general framework, which is something I'm working on now, not just for tabular and images in this case, but in general for all cases. And uh, and then this could lead to applications of this for detecting domain shifts or data drifts for continual learning, when you could end up learning and adding new prototypes to the stack, or even changing certain thresholds, deleting some prototypes, and so on, depending on different metrics, all grounded from the explanations and results. So yeah, that would be it. Thank you. Thank you for the time.